Okay, so today we need to do background for what we're gonna do later on. I'm not even gonna tell you what it is later on, because I'm gonna get you there, okay? So what we're gonna do is we're gonna talk about circles. We're gonna talk about circular motion, okay? So let me start by drawing a circle. Let's see if the computer will help me. So I'm gonna draw a circle here. That's not too bad. And I'm gonna put the X and Y axis in there. You hopefully remember that a circle, if I can remember the fancy term that the math teachers use, that a circle is the locus of points equal distance from a single point. If I remember, locus is like group of points. Why they call it a locus seems a little locus to me, anyway. But let's talk today about how we would find different things about this circle, but only related to theta. So if theta, for instance, is from here to here, there's theta. This is the x-axis, the y-axis, obviously. The first thing we do in physics is we talk about position. Well, let's talk about the x and y positions relative to theta around this circle. So here's theta, and we're going to do 0 degrees, 90 degrees, 180, and 270. Okay? And we're going to find the x positions and the y positions for all of those. Okay? Gotta get the nice, there we go. So, the x position at theta equals 0, the x position would be a maximum, wouldn't it? So I'm going to call it a positive. Well, the x position, but the y position, would you agree the y position is 0? Right? It's right on the x-axis, so there's no y position there. How about when it's at 90 degrees? When it's at 90 degrees, it's up here at the top. Well, x now equals 0. But y is at a positive. All right? 180 degrees, way over here. Well, x is a negative, and y is 0, right? We're on the y-axis. Now we go below to this point. Y is a negative, but x is 0. Well, let's go ahead and graph those on a chart, on a graph. See what they look like, okay? Because realizing from here, it's not going straight from positive to 0, it's changing gradually, which is going to be a smooth graph. Well, here's our x graph and our y graph. And we'll go ahead and get our 4 positions here, try to make them look pretty. Okay? Well, the x graph starts at a positive, then it goes to 0, then it goes to a negative, back to 0, and once it comes back, it would be back at a positive. Well, connecting those, you're not surprised to say that that's a positive cosine graph. Well, how about the y position? Well, the y position goes 0 positive, 0 negative, 0, which is, of course, a positive sine graph. So we could say, oh, so our x equation would then be cosine of theta. And our y graph would be sine of theta. That makes some sense. So we start off at theta equals 0, we have a positive, right? And that would give us 1. And then when cosine is 90 degrees, you can try this on your calculator, the cosine of 90 degrees is 0. The cosine of 180 degrees is negative 1. The cosine of negative 90 or 270 is 0. That works. However, we as physics people look at that and say there's an issue here. The issue is that this column here has the units of meters. And the cosine of theta has the units of percent, which is not a unit. And meters can't equal nothing. If the left side is meters, the right side must be meters. So this is saying that here, whatever meters they are, then 100%, the cosine of 0 is 1, or 100% of it is in the x direction. Well, now 0 of it is in the x direction, negative 100%, so it's in 100% in the negative direction, 0. What is this thing that's changing? And this position is the radius. So we put in r. Let's say the radius is 1, the unit circle. Well, at theta equals 0, then your x is 1 meter. That makes sense. Okay, let's say that r equals 1 meter for the unit circle. Then the cosine of 0 degrees gives you positive 100% of the radius is in the x direction. And 0% of it is in the y direction. Now you move up to 90 degrees. Let me get over here because you're looking at the equation. When you're up at the 90 degrees, well, the cosine of 90 is 0. 0% of the radius is in the x direction. And 100% of the radius is in the y direction. That's what that means. Now, the radius doesn't have to be 1. The radius could be whatever value you want to put in there. Okay? Well, what about velocity? What about instead of just finding the positions? We've now found the position of all of that depending on the angle. Oh, before I forget, let's just do a special mark. Let's just call this 30 degrees. Okay, let's just pick 30 degrees and see what we get here. If you put in the cosine of 30 degrees, you get 0.87. It's 0.866 something, right? So it says that 87% of r is in the x direction. So that would be 87% of that would be x. And how much of it would be in the y? Well, the sine of 30 degrees, the sine of 30 degrees is 0.5, which is 50%. Hey, look, that's halfway up to the top. Half of the radius is in the y direction, or it's projected on the y, okay? Now let's talk about this object moving. What if the object's moving? Let's go ahead and draw another beautiful circle here. So we have this object that's moving. We'll say it's moving in the counterclockwise. And let's take these 4 positions once again. Right now, the object is moving up in the positive y direction. When the position is at 90 degrees, the object is moving to the left in the negative x direction. At 180, it's moving in the negative y direction. And at 270 degrees, it's moving in the positive x direction. Let's write those down. Actually, let's write them down just to make sure that we don't have any disagreements here. So we have Vx and Vy at 0, 90 degrees, 180, 270. We all know that we're talking about degrees. All right? So let's look at our x directions first. At this position, where theta equals 0 degrees, we have no x component of the velocity because it's only moving up. So this is 0. But the y component has a positive velocity, positive v actually. At 90 degrees, we get a negative v. But the y component is 0 because it's horizontal. At 180 degrees, we have negative y component, but 0x component because it's vertical. And at 270, we get a positive x and 0y. Let's go ahead and graph those. This is Vx and Vy. And we get 0, negative, 0. And that's enough to draw it right there. And this one is positive 0. All right, so what do we get? That's a negative sine graph. And this one is a cosine graph. Is it positive 0, right? Yep. That's a positive cosine graph. Which tells us that the x component of the x velocity will be negative v, whatever the velocity of the object is, times the sine of theta. And the Vy will equal v times the cosine of theta. Let's see if that makes some sense. So look at this one right here. Let's say the velocity is 2 meters per second. Pick a number, right? And again, I realize that we're using a v for velocity, and velocity has direction as well. And we're saying the object's at constant speed. The velocity is changing because it's moving directions. This basically doesn't give you that. It just gives you the components. You could put those together and find the velocity at any given angle, okay? So let's say we have 2 meters per second, just for instance. And let's say the cosine of 90 degrees. So at the top position, the cosine of 90 degrees is 0, which says 0% of it is in the y direction. Correct, because it's horizontal. None of it's vertical. But what about halfway? Let's pick a special number here. Let's say good old 45 degrees, our buddy. 45 degrees. And you might say, oh, well, half of it's in the y direction, half of it's in the x direction. No. It is true that they have equal x and y components at that point, but it turns out that the sine of 45 degrees equals the cosine of 45 degrees, and that is 0.707, right? Or 71%. 71% of it, I can't do 0.71, but 71% of it is in the x direction. Or I guess the correct way of putting this is the x velocity is 71% of the total. The y velocity is 75% of the total. And you might say, how does that equal 1? 71% and 71% does not equal 1. But it's a right triangle. If this is 0.71 and this is 0.71, by Pythagorean theorem, this should be 0.71 squared plus 0.71 squared, which equals 1. I'm being verified over here, students doing that right now. Or it'll be very, very close because we read it. And I got a thumbs up. Because somewhere, yeah, I can't do it with my mouth right now because of the mask, but I'll have to be more expressive with my eyebrows. Somewhere, someone told you that the cosine squared theta plus sine squared theta equaled 1. Because x squared, or a squared plus b squared equals c squared. That's just Pythagorean theorem. Or this percentage squared plus that percentage squared will give you 100%. Okay? Now that we've got the velocities, let's find the acceleration. But one more time, we need a beautiful circle. My circles are doing pretty good today. That one got a little oblong over there. So much shame. When I go to the Circle Academy, they're going to say, terrible! Right? Well, now, let's talk about acceleration. Since an object's in a circle, the acceleration only points to the center of the circle. We call it a centripetal acceleration. Well, where theta equals 0, it'll be pointing to the inside of the circle. To the inside of the circle. Those are our directions of the centripetal acceleration at those 4 points. Well, let's go ahead and draw it. So the x will be negative x, 0y because it's not pointing up or down. At 90, negative y, 0x, positive x, 0y, positive y, 0x. Let's go ahead and graph those now. And I get negative, 0, positive. And here I get 0, no, yeah, 0, negative. So that looks like a negative cosine graph, and that looks like a negative sine graph. Which means AX equals the acceleration of the object times the negative cosine of theta, and the y component equals negative a sine theta. I would like to take all of these equations that we just derived, and I would like to move them over to the side and look at them together. We have to shrink this up, maybe a little harder for you to see right now, okay? So we have x equals our cosine of theta, so we'll put all of our x equations here. We'll put our y equations here, and then we're going to take a look at them together and see what kind of cool things we see. So y equals r sine theta. We get Vx equals, there's our Vx, negative V sine theta. Vy equals V cosine theta. Our acceleration in the x direction equals, there we get negative A cosine theta. And A and the y equals, you see it down there? Negative A sine theta. Now, before I go doing, there's supposed to be an equal sign here. I apologize. Let me go ahead and get that to where it looks kosher here. We don't want anybody to go all weird on me there. I want to draw something for you before we make a little comment here. Well, actually, I guess we can do this here. You should now remember that the velocity function is defined as, I'm putting 3 lines, that means is defined as dx dt, or the derivative of the x function. Likewise, the velocity in the y direction would be the derivative of the y position. The acceleration is dv dt. Now, before I make one more comment, we're going to go down here and prove something. I am of the opinion that if you can do something to always know what something is and not memorize a bunch of facts, it's better, because I got a lot of stuff going through my head. I know some of it may not be all that cool, but you know, it's cool to me. And you know, like sometimes now that I've got a little kid, it's like Veggie Tales, or you know, little things that kids sing all the time. Yeah. Anyway, so here's something that I use to memorize the derivatives of sine and cosine. I don't memorize that. If you were to walk up to me in the middle of the road and say, "Hey, Mr. Murray, how's it going? Hey, how's it going, Joe? Hey, what's the derivative of sine of theta?" I would go, "It's this." I would work it out in my head real quickly. I don't memorize it. There's no reason for it. You got enough to remember, okay? So here's, let me see. So we have cosine of theta, which looks like, let me get these lined up so we can keep everything looking, so we can actually see them one on top of the other. That's actually should be enough. Cosine goes here. Did I do that right? No, I'm getting a little sloppy. So it goes here, there, there. That's a cosine graph. It's too big. I have to do it one more time. I'm sorry. There we go. Am I kind of doing it? Okay. Then it goes 0. See, that's a 0 slope, right? And derivative is slope. 0 slope, negative slope. 0 slope, negative slope. It'll go back to 0. Well, that's a negative sine graph. My slope there is negative. It's flat. My slope is 0. It's going up. The slope is positive. Slope is 0. Hey, that's a negative cosine graph. 0, positive. Then it'll go back down to 0. And that's a positive sine graph. And then positive 0, which is again the cosine graph, and the whole thing starts over. This is derivative. Make this a little bigger so you can see it. So this is derivative. And obviously, if you wanted the integral, you would go the opposite direction. I don't memorize it. There's no reason to. I could have done that faster, by the way, just gone 0 negative. I could do that and you got to go, that makes it better, right? Anyway, so that's how you figure out what they are. So let's just, let's take this. And actually, how can I see this all at one time? So notice, cosine goes to negative sine. Ta-da! Sine goes to negative sine goes to negative cosine. Ta-da! Sine goes to cosine. Ta-da! I'm running out of room up here. Let's see how high I can go. And cosine goes to negative sine. Ta-da! Ta-da-da-dum! That's the big finale right there. Wow, check that out. These are actually fitting what you learned in calculus. This, what we just wrote, even though we did it for just the points around the graph, these are the equations of motion for an object moving in a circle when all you're using is theta. Now later on we're going to put time into this, okay? But for right now, we're just gonna do theta. I hope that people can see this. Unfortunately, as I'm looking at my camera here, there's some reflection. It's not gonna be perfect, okay? That's best it's gonna be. Yeah, now, last thing I wanna end with. If I come over here. In all cases, when you are doing things in physics, you have a starting information, or your starting descriptor is what we call it. And generally, it's its position. Doesn't have to be. For the kinematic equations, the easiest way to be able to derive all of the kinematic equations is to say your acceleration is constant when it comes to the y direction, and there's no acceleration in the x direction. Okay? But here, if we do this, that x equals, and make this a little bit bigger, hopefully it's easier to see. So x equals r cosine of theta, y equals r sine theta, and then you should just, once you have that memorized, which you can do from a circle real quickly, right? Well, v equals dx dt, and we just found out that cosine goes to negative sine, so we get negative r sine theta. And I'm going to put that as an x here. And vy equals r cosine theta. I think I got that right. The funny thing is, I'm not remembering this because I don't memorize it. I've told you that, right? So even this 1 minute here, I'm not memorizing it. And then my acceleration in the x direction is the v dt, but it's dvx dt, which equals, that's negative cosine, I believe, right? So you just derive them from what you already have. Oh, no, that's not r. I did mistake. Mistake! That's vy, or sorry, that it was r, wasn't it? No,
I thought
that's
sine.
v. Yeah, v, and this is a sine theta. Double check that I got those right.
I thought
Cosine, negative sine, cosine, cosine, yeah. Except for this one is not r, this is v. Right? There we go. By knowing your descriptor, or the one bit of information you know for sure, you can easily get the other ones by just taking the calculus. End of discussion for today.